In this next section, we're going to look at polynomial functions, and we're going to do similar things to what we did with the quadratics, in that we're going to graph them and be able to find information about the polynomial based on the properties and the graph of the function. Okay. So to start, let's look at what we mean by a polynomial function. So first off, this notation is probably daunting for some of you, and you don't need to worry about the notation in so much as this means that I'm looking at some coefficients times some single variable raised to integer exponents, where the integer exponents are positive. So a n x to the n, a n minus 1 x to the n minus 1, all the way down to a1x times it plus a0. This is a polynomial function. So as I said, all of the coefficients, all the a sub n's, are integer coefficients. A0 is a constant, so that can be an integer as well. A sub n not being 0 just means that I have some highest degree and it's not 1. So it's not a linear equation, it's not a quadratic equation. I'm looking at something bigger than that. A sub n is our leading coefficient, and n, the power on the first or highest power term, that's what we're going to call the degree of the polynomial. Okay, so two really nice things about polynomial functions is, first off, we consider polynomial functions to be continuous functions. And what that means for us first is that the domain is all real numbers. So I can put any number I want into a polynomial and I'm going to get a real number out. Okay, and then the second part of that is there are no breaks, holes, or lifts in the graph. So if I were to draw a graph of a polynomial function, I can draw it without picking up my pencil. Okay, that's all this means. And keeping those two things in mind makes graphing polynomials fairly nice in the sense of some of the properties that they have. Okay, so one of the first properties we're going to look at is the end behavior. And the end behavior is just what it sounds like. If I'm looking at a polynomial's graph, I'm looking at what the ends are doing to determine the end behavior. Okay? And there's a couple of ways to determine this. So some of this notation may look a little new to you, and so I'm just going to kind of go through it as I go through the different pieces for the end behavior. So now, as I said, end behavior is what happens far out towards the ends of the graph. So I'm not looking at what's happening around the origin. Many things could be going on around the origin, or even not so far out from the origin. But here when we talk about end behavior, we really mean as x is way off towards infinity or x is way off towards negative infinity. Okay? So if my degree of my polynomial is even and my leading coefficient is greater than 0, then y, meaning my function value, is going to go to infinity as x goes to both positive and negative infinity. Okay? Pictorially, all that means is if I'm looking far out on the graph, as x's get bigger, the y values are getting bigger, and as x's go to negative infinity, the y values are going to positive infinity. And notice here I didn't draw anything in the middle, because again, the end behavior is only looking at the ends of the function. So there could be all sorts of things going on in here. Okay? So an example of a function that would have this type of graph would be something like p of x equaling 3x to the fourth plus 2x cubed minus x plus 5. Okay? So if I look at it, the degree on the polynomial, meaning the highest power term, is even, and the leading coefficient is positive. Okay? If n is even and a sub n is less than 0, then y is going to go to negative infinity as x goes to both positive and negative infinity. Okay? So this one is just going the other direction. If I have a polynomial where my n is even, then as I get further away from the origin, both of the ends are going to go towards negative infinity. Okay? And again, an example of a polynomial here would be something like, so I need a negative coefficient, so negative 2x to the fourth plus 3x squared minus 7. Okay? And notice for both polynomials, it doesn't matter what those remaining terms look like. All I care about is the leading coefficient and the degree of the polynomial. Okay? If n is odd and my leading coefficient is greater than 0, then we actually get that the n's are going to do different things. As x goes towards infinity, the y values will go towards infinity, and as x goes to negative infinity, the y values go towards negative infinity. So for this one, if our n is odd, so for example, let's say our p of x looks like 3x cubed plus an x squared minus 5x. Okay? So the odd degree tells me as x gets big, the values here are going to get big. And if x is negative, and they get more and more negative, then the values there are going to get more and more negative. Okay, so there's a picture of what our n behavior will look like for that one. Okay. And then the last case is if n is odd and our leading coefficient is less than 0, again we get them going in opposite directions. Y will go to negative infinity as x goes to infinity, and y goes to infinity as x goes to negative infinity. So here we're going the other direction. Okay, so an example of a polynomial like this would be, say, a negative 5x to the 7th plus 6x to the 4th minus 3. Okay, so my leading coefficient is negative, and my degree is odd. So here, if I'm putting in positive x values, these are going to get more and more positive, but the negative 5 makes them become negative. And if I put in a negative x value, these are going to get more and more negative, but then multiplying by the negative 5 makes them become positive. Okay? So there's the 4 different ways that my n behavior can look depending on my polynomial function. Okay? And that's it. There's no other ways we can have for n behavior. So either it's going to increase to infinity or it's going to decrease to negative infinity. But for a polynomial function, those are the only 2 options. Okay. Another property that we're going to look at for our polynomials is the real zeros. And the reason I mention these, you'll see a little bit later in this video. But in order to graph polynomial functions, if we think about what we did with some of the quadratics and linears, we needed to talk about intercepts. And for these, we're going to talk a little bit more about real zeros. And so if p of x is a polynomial and c is a real number, then the following are equivalent, because you're going to hear different terminology. And so just knowing that these things mean the same thing is helpful. The first is if c is a 0 of p of x. So what does a 0 mean? It means that if I solve the equation p of x equals 0, I'm going to get a solution of x equals c. Okay? It also means that if I'm trying to factor p of x, x minus c turns out to be one of the factors for that polynomial. And lastly, if I'm saying that c is a 0 of p of x, another way to say that is c comma 0 is an x-intercept for the polynomial. Okay? So when we're talking about real zeros, we're just meaning when I'm looking on the graph, the places where the function crosses the x-axis, these are all zeros of the polynomial. Okay. So looking a little further into our polynomials, one of the properties that comes out from the fact that our function is continuous and that there are different types of n behavior is this notion of intermediate values. Okay. The intermediate value theorem basically tells us that if I'm looking at a polynomial function and I have 2 points, which I'm going to call p of a and p of b, so a and b are the x values, p of a and p of b are my function values. If these function values have opposite signs, so one is positive and the other is negative, then the intermediate value theorem tells us that there has to be a value c, an x value c, such that p of c is equal to 0 as long as c is between a and b. Okay? So if I'm looking on a graph, what this is saying is if this is my x-axis and I have some a and some b such that the sine of a and the sine of b for the function values are opposite, so one is above the x-axis and the other is below, because it is a continuous function, there has to be some point in here c where that p of c is equal to 0, meaning it is a root of our polynomial. Okay. Now, it does not say that if both are above the axis or both are below, it has to cross the x-axis. So if you go back to what we were saying about end behavior, if my ends are both going to positive infinity, there's nothing saying that this graph has to cross the x-axis. However, if I'm looking at something where my ends are going different directions, then there's got to be at least one point where that crosses. There could be many, so I could have something that does, something like that, where I have more than one point that crosses. But there's got to be at least one, and that's what our intermediate value theorem says. Okay. So looking a little bit more into our zeros, another notion that is going to be helpful in graphing your polynomials is the notion of multiplicity. Okay? And basically the multiplicity of a zero says the following. If x minus c raised to the n power is one of the factors of our polynomial, n can be an integer, it could be 1, it could be 5, it could be any integer, positive integer value. But if that's a factor of our polynomial, then c is a 0. So we said this in our last little statement there. But more importantly, it has a multiplicity of n. And so what that just means is if I'm looking at my p of x, I can write it as x minus c to the n times the other factors, or I can write it as x minus c, x minus c, x minus c, n times the other factors. And what this means is when I set this equal to 0, I'm going to get x equal to c n different times. So there's going to be n roots of c, or n x-intercepts that are c. Okay? If n is even, then the graph of my polynomial is going to bounce off the x-axis at that particular 0. So if I'm looking at an even multiplicity, so for example, if I'm looking at p of x equaling, say, x minus 2 to the 4th, this just means that if I look at x equal to 2, the graph is going to bounce off the curve at the x-axis at that point. Okay? It doesn't matter how big that even number is. All that's going to do is change how flat it makes the graph, if you remember from our transformations. But in general, it means that it's not going to actually pass through the function at that point. It just gets there and goes back off. If n is odd, then the graph is going to pass through the x-axis. So if my p of x looks like x minus 2 cubed, then over here at x equals 2, what we're going to find is that it's going to do something like that. So instead of staying on one side of the x-axis, it's actually going to pass through it. Okay. All right. So in order to graph a function, a polynomial function, we're going to put all of these things together. And again, there are going to be instances where just knowing this information is not enough. So here I'm talking about basic graphing. If I've got a nice polynomial function that I can factor, then I can use the Bayesian graphic techniques to graph the function. And what that is I'm just going to find the zeros. So we're going to go through and we're going to factor the polynomial down and get it in terms of its linear factors if possible. And also the y-intercept. And I'll explain the y-intercept when we do some examples. Okay? So I'm going to find those things. I'm going to determine the multiplicity of the zeros. So I want to determine if each of those are even or odd, because that's going to tell me what's going to happen at that point on the graph. And then I want to determine the end behavior. So like we said before, I want to know, are the ends going upwards? Are they going down? Are they doing opposite things? I want to know so that I can determine what happens to my y values as my x's get further and further away from the origin. And then lastly, I'm going to use that information to sketch the graph. And again, this is a sketch. I'm not point plotting at this point. I'm not getting exact values for every single x value in there. It's just a sketch. So it's giving me the general behavior of the function at the critical points, which are our intercepts, and also what the end behavior is doing. Okay. Now, one last thing to note. One of the things we talked about in terms of quadratics was once we figured out where the vertex was, we talked about local extrema, meaning maximum and minimum values. Now, in this case, we're not actually going to find those just yet. That comes later. But if p has degree n, what we can say is then the graph of p has at most n minus 1 local extrema. And again, the reason we say at most is because if I look at two different cubic polynomials, so let's look at a basic cubic like that, x cubed, and then let's look at y equals, say, x minus 1, x plus 1, x minus 2. Okay? Y equals x cubed is one of our basic curves. We know as x goes to infinity, it goes to positive infinity. As x goes to negative infinity, y goes to negative infinity. We had some nice points of 1, 1, negative 1, negative 1, and it had that basic chair function. Okay? And in this case, if we look, there are no local extrema. This graph kind of increases everywhere. There's no places where it's changing from increasing to decreasing. So this one doesn't have any extrema. Okay? If we look at this graph, so x equals 1 is going to be one of our intercepts, x equals negative 1 is going to be an intercept, and x equals 2 is going to be an intercept. So we've got these points here, and based on what we just did with multiplicity on each of these is 1, so it's going to pass through. I can also see that the leading coefficient here, if I multiplied this out, would be x cubed. So degree is odd, leading coefficient is 1, so I know it's going to do something like that for the ends. But then passing through each of these points means that my graph is going to have to do something like that. Okay? So here we can see I've got two cubic polynomials. One of these doesn't have any extrema. The other, if we look, there's certainly a maximum in there and a minimum in there. So this one has one of each extrema. One of the things I want you to think about before you go into the next part of this video when we start graphing is, in this case I've got 0. In this case I've got 2, one max and one min. We've already said you can have at most n minus 1. So if my degree is 3, this is the most I can get. Can you find a third degree polynomial that has exactly one extrema? Okay? So think about that and why we say the at most there. So think about if there's ever a way I can get a third degree polynomial that has exactly one extreme value, or one that why I can't have a third degree polynomial that has 3 extrema. Okay? So think about why this no. So let's look at some examples of graphing polynomials using just the basic techniques. So in this first example, we've got p of x equals x cubed times x plus 2 times x minus 3 squared. In this example, our polynomial is already factored for us. So we've already can pull off the roots of this, or the zeros of this polynomial, fairly easily. Okay, so remember, once I have the factors, I know exactly what my zeros are. So the zeros are going to be, well, if x cubed equals 0, x will equal 0. If x plus 2 equals 0, x will equal negative 2. And if x minus 3 equals 0, x will equal 3. Now again, once I get the zeros, I also want to look at the multiplicity. And again, if it's in its factored form, then I know exactly what the multiplicity is. So the multiplicity for x equals 0, again, is just the power there, so 3. for x minus 2, or x equaling negative 2, my multiplicity was just 1. And for x equaling 3, my multiplicity is 2. Okay. Now again, along with my zeros, should also find my y-intercept. And this just gives me a reference on the graph as to what's happening at that origin, or at least when x is equal to 0. So if x equals 0, we can see I'm going to get 0 cubed, 0 plus 2, 0 minus 3 squared. Well, in this case, I don't really care what those are because I'm multiplying by 0. So my y-intercept is 0, 0. Okay. For end behavior, we can see that's the leading coefficient. And again, for these ones that are in factored form, it may be useful to write out what that first term is going to look like. So in this case, I can think x cubed times x squared. Okay. In this case, I can see that it's going to have a degree of 3, 4, 5, 6. And my leading coefficient, well, x cubed times x squared, that leading coefficient is just going to be 1. So if I'm looking at my end behavior, degree is even, leading coefficient is positive, which means my ends are both going to positive infinity. Okay? So now I'm going to put all this information together and get a picture of the graph. So if I'm looking at this, again, we've got some intercepts there. So again, I'm going to start by labeling my graph. Okay, I've got x equals 0, which we knew was 0, 0, x equaling negative 2, and x equaling positive 3 are all my x-intercepts or zeros of the polynomial. I know that my end behavior is going upwards at the outermost roots, and I have that the multiplicity tells me what it's doing at each of them. So at negative 2, I can see the multiplicity is 1, so it's going to pass through that point. At 0, my multiplicity was 3, so again I'm going to pass through. And then over here at 3, my multiplicity is 2, so it's going to bounce off. Okay. So there would be a sketch of my graph. And again, it's a sketch because we don't know where this local minimum, or this local maximum is. We just know they exist. And again, if I were to actually graph this a little more detailed, we would want to find those points and then actually sketch this a little more accurately. But there is a sketch of our polynomial p of x. Okay. All right, so let's look at our second example. So this one, the main difference here is I'm no longer given a factored polynomial. So the first thing I'm going to want to do here is factor this polynomial. So I'm going to pull an x squared out of everything. So x to the fourth minus 3x cubed plus 2x squared. I can pull an x squared out, and I'm left with x squared minus 3x plus 2. And from there, I can see in that set of parentheses, I can factor that to an x minus 1, x minus 2. So there's my p of x. And again, once I'm there, I can automatically find my zeros. So my zeros, okay, are x equals 0 from the first, x equals 1 from the second, and x equals 2 from the third. And our multiplicity, again, we can get from this factored form. So for x equals 0, my multiplicity is 2. For the others, my multiplicity is 1. Okay. Again, we should notice when x is 0, my y-intercept is also 0. And for our end behavior, this one is easier to see because we have the polynomial form. So our degree is 4, and our leading coefficient is 1. So again, I'm looking at positive ends on my end behavior. Okay? So with that, I can then graph this. So again, same thing. When I go to graph, I'm going to start by labeling my picture. I'm going to go ahead and put in my intercepts. So 0, 0, when x is 1, and when x is 2. So there are my zeros of the polynomial. My end behavior, so again at my outermost intercepts, my end behavior is going to go up. And then we can see with our multiplicity, at x equals 0, it's going to be even, so it bounces off my polynomial there, my graph. 1 and 2 are both odd, so they're going to pass through. Okay. And again, same thing. We can see there's a max and a min there. We don't know what they are at this point, but there would be a sketch of our graph. Alright, so for this next example, let's look at a slightly bigger polynomial. Okay. So this one we're looking at a 6th degree polynomial. So p of x equaling x to the 6th minus 2x cubed plus 1. And I picked a slightly bigger one that doesn't have a lot of terms because, again, we're going to have to factor this out in order to determine what the graph is doing. Okay. And for these, this is where, again, if you go back to your factoring, whenever you did this, either in prerequisite course or in the prerequisite material of this class, you'll see that looking at this, even though it's not a nice quadratic equation, it is in its quadratic form. And so we can factor this as x cubed minus 1 and an x cubed minus 1. And then from there, I can factor those using my difference of cubes. So that says it's going to be an x minus 1, x squared plus x plus 1. And then I'm going to get the same thing when I factor that one. So these become squares. Okay. Now the difference between this one and the last one is that last one, once I got that quadratic factor, we could factor it further. In this case, this factor right here does not factor further. Okay? So that tells us two things. One is that I'm probably not going to get real roots for that, or real solutions of that polynomial. And second, that means my graph isn't going to be as easy to indicate what's happening at those values. Okay? And so here, when we look at the zeros, again, you're thinking set these equal to 0 and solve. From this one, I get x equals 1, and we can see that the multiplicity there is 2. But over here, if I try and set this equal to 0, I get imaginary numbers. Okay? So this is my only real 0 for this polynomial. Okay? I still want to find the y-intercept. So if I plug in x equals 0, we can see that I'm just going to get a value of 1. Okay. And then for my end behavior, again, degree is even. My leading coefficient is positive. So here again, my end behavior is going off to the positive infinity. So, looking at my graph on this one, I have a y-intercept of 0, 1. We have an x-intercept of 1, 0. multiplicity there is even. Okay. I only have the 1 point, so my end behavior has to go upwards from there. And that matches with the fact that it is an even multiplicity. But here you've got to be a little careful because this looks a lot like a parabola. Okay? And again, like I said, we are sketching at this point, so it's not going to be exact. But if we think about it, we've got 2 squared, or 4 roots, that aren't playing a part in here. At least not from what we've determined in terms of the real values. So instead of just making this look like a parabola, what we're going to do is we're going to take into account that there are other roots, they're just not real. Okay? I'm still going to have the same end behavior, but coming from my intercept here, there's going to be some pieces of the graph that make it not as smooth. Okay, so you can see I drew in kind of bump there and a bump on this side. Okay, and those bumps come from the fact that I have imaginary roots in there. It's what makes the curve not as smooth as what we've seen in the last few. Again, in this case, I don't know exactly that those bumps are there. They could be over in this area or over in this area. But I want to indicate on there that there are other roots, and it's not just a parabola. Okay? And again, we get that from the fact that there are some imaginary things happening. Okay? Later sections of this textbook will go into the complex numbers a little bit more, because this course doesn't actually need it for what we're going to be doing. We'll leave it at that. And for those ones where we actually want you to graph this a little more explicitly, we will have other methods for getting where those abnormalities occur. Okay. All right, so let's look at one last example. And so this one, we're going to look at another polynomial form. The difference here is my leading coefficient isn't just 1 anymore. So we're going to change things up a bit. So again, looking at my polynomial form, so 2x cubed minus x squared minus 18x plus 9, I can see that I'm going to need to factor it. And this one, because I've got the 4 terms there, probably going to factor by grouping. So I'm just going to group these first 2 terms together, group those last 2 terms. I can pull an x squared out of the first 2, and I can pull out a negative 9 from the second 2. Okay. From there I can see my 2x minus 1 is my common factor. I get an x squared minus 9, but that can factor further. So we'll get x minus 3, x plus 3 times the 2x minus 1. Okay. So our zeros, we have x equaling a half from the first one, x equaling 3 from the second, and x equaling negative 3 from the third. Nicely, for all of these, my multiplicity is just 1. Okay. End behavior. Oops, sorry, almost forgot our y-intercept. In this case, our y-intercept, if we plug 0 back into our polynomial form, we see that we get 9. For the end behavior, here our degree is 3, and our leading coefficient is 2. So odd degree this time, even leading coefficient, or positive leading coefficient. So we're looking at end behavior that has opposite sides. Okay. So for our graph on this one, again, we'll start by labeling our graph. Okay. So our zeros, we have 1 at a half, 1 at positive 3, and 1 at negative 3. And our y-intercept is up here at 9. Our outermost ones to the left there, we're going to negative infinity. The right, we're going up to positive infinity. Okay. All of our multiplicities are odd, so we're going to pass through each of them. So coming from the negative side, I'm going to pass through the 3 there. But notice, to get to this 1, I'm going to have to go through my y-intercept. So here I'm going to actually change the slope here just a little bit, because I'm going to come through that point and then go to negative infinity. Okay. Now it could be I come up and this is a high point on this side and comes back down. But since that's so close, I'm going to draw it this way. And then at a half, again, I'm going to pass through. When I get back to positive 3, I'm going to pass through again. And so there would be the sketch of my graph. So in this first section, like I said, you're going to be asked to do something similar to what you see here, where you are given different polynomial functions, both in their factored and in their polynomial form, and you have to go through and be able to come up with a picture for the graph. Again, to do that, you're basically looking at what are the zeros, what are their multiplicities, what's the end behavior, and then knowing the multiplicity and how the end behavior react to that information, what the graph looks like.